lecture of microscale transport process. What we have been discussing in the last class is flow of two phases, flow of two immiscible phases through a microchannel. That means flow of droplets or bubbles, and what we talked about is a relationship which is referred as Bretherton's model or Bretherton's equation to find out what would be the pressure drop if a series of droplets or bubbles flow through the microchannel. The results that we got, if we try to summarize the results, it would be something like this. The pressure drop that we talked about is delta P is equal to 0.64 r into 3 capillary number to the power 2/3, and we said that this is there is a theoretical basis to say that this would be the dependence. So, if somebody wants to find out what would be the pressure drop along in a microchannel, this would be the pressure drop, and the thickness of the annular liquid layer at the mid plane. That means, if the bubble, if this is one axisymmetric bubble placed in the microchannel, then the thickness at the mid position of the bubble, this thickness of annular liquid layer, that is referred as, oh, I'm sorry, this is not delta P. I mean, I wanted to say this as H infinity, that thickness. Okay, this is the thickness, this H infinity, and the delta P is equal to 10 r by sigma into capillary number to the power 2/3. This is the relationship that we had talked about in the last class. What I have on top of it, then we discussed few things. For example, we discussed about this H infinity R C divided by H infinity H infinity 0, where there is these bubbles are not exactly separated by spherical cap, rather it is a very thin lamella that separates the two droplets or two bubbles. So, for that, this R C was the contact radius, and we discussed about what would be the functional relationship, and for a non-circular channel, how you will address this. So, I talked about these in the last class, at the end of the last class. On top of this understanding of Bretherton's equation or the solution of Bretherton's the analysis, we have another point to be noted here before we move to other topics, is something called a Bretherton scaling. Bretherton scaling. Okay. The Bretherton scaling is something like this. One may note that the curvature at the cap is somewhere similar to 1 by r. What is r? R is the radius of the tube, radius of that microcapillary. So, it can be this can be approximate, this is an approximate one, definitely. I mean, this is not true, but this is an approximate one. On the other hand, the film curvature is written as second derivative of h, that means d square h dx square. Now, this is non-zero in the transition, this is non-zero in the transition region between the caps and middle parallel section of the bubble. Okay. So, this hxx now it can be said in that these two curvatures are, they are to be balanced at the transition. So, what was done in Bretherton scaling is they have equated this. Basically, they said that if somebody wants to know the scaling, if somebody wants to know, say I have these parameters that I have, this is the dimension of the microchannel, this is what I have. Now, can you tell me what would be this value of h infinity, okay, or what would be the value of h? What would be the value of h? Can you give me some idea of the average h that is there? I mean, instead of going through these analysis, I mean whatever we discussed in the last class, simply by looking at it as a problem of scaling, if somebody gives me an idea that okay, this is the capillary number, this is the radius of the microchannel, and this is what I have flowing through this microchannel, can you tell me what would be the average value of, or an approximate scale? For example, is it 10 to the power minus 4 or 10 to the power minus 1 or 10 to the power 3? Can you give me some idea what portion would be occupied by the liquid and what portion would be occupied by the gas? So, if can somebody give me this idea? That is something which is which if somebody is interested in that fact rather than a rigorous solution, what the way it has been done here is these has been equated with 1 by r. That means, what they are saying is okay, in some portion it is d square h dx square, and at the end this is going to be close to 1 by r. So, if somebody wants to know what is the approximate h as far as this bubble and annular region is concerned, then what one should do is he should equate this with this and try to find out how the h depends. Now, what they have done is they have so they equated this, they are trying to find out what would be the scale of h, okay, what would be an approximate order of magnitude as far as this h is concerned. Okay. If I talk about h divided by the radius or 2 r of the microchannel, what is that order? Is it close to 0.5 or is it close to 0.5 into 10 to the power minus 5? So, that order, if somebody wants to know, probably this analysis could be useful. So, that is what has been done in Bretherton scaling. Now, this has been probably was integrated with some boundary condition, maybe at x equal to 0, x starts from here. So, at x equal to 0, dh dx equal to 0. So, with these use of these boundary conditions, I mean they ended up with very likely dh dx is equal to x by r, and then they further integrated. I mean what they have, what the bottom line is that they have said that h is proportional to x square divided by r. These relationship they have come up with by integrating it twice. Okay. It is not a rigorous analysis. Once again, what they have, what this the objective here is to find out what would be the scaling. All right. So, given this, now if somebody wants to find out what would be the viscous stress, and relate viscous stress with pressure drop, what he will write in that case is mu du dy. Now, I make this du dy, I write it as u divided by h. U divided by h at at y is equal to 0, the velocity is 0, at y is equal to h, the velocity is u. So, it is mu u by h. So, once you have mu u by h, so that means it is basically du dy. Now, what you do in this case is when you relate viscous stress, with pressure drop, then what you would be doing is mu u divided by h, that divided by h is proportional to dp dx. That is what you would be writing, and you know that this delta p, you know this on top of this, you know that this delta p is equal to 2 sigma by r. So, from this you can conclude that this mu u by h divided by h is proportional to sigma by r x. All right. So, on one hand you have this relationship, on the other hand you have said that this h is proportional to x square over r, or you can say here x is proportional to square root of r h. So, this is another relationship coming from here. Okay, x is proportional to square root of r h. So, x is proportional to square root of r h, this is what you have, and on otherwise you have this relationship. If you club them together, what you get is h square divided by r x is proportional to mu u divided by sigma, which is basically, that means it is proportional to capillary number. Okay. And on top of that, I have this relationship x is proportional to square root of r h. Now, if you put this in here, what you get is h is proportional to r capillary number to the power 2/3. All right, and also x is proportional to r capillary number to the power 1/3. So, you have some idea what would be this average h. Okay, so, you have some idea that you are introducing you are using immiscible phases into the microchannel, but it would be splitted into there would be an annular portion for the liquid part, and then you will have the other part, droplet or the bubble at an axis symmetric location. But what are their dimensions? Without getting into a rigorous calculation, you can get some idea of these dimensions simply from scaling. Of course, this is a scaling analysis. I mean, what this means is, if somebody knows the capillary number, okay, then it is say for example, for a bubble speed of 1 micrometer. Okay, of course, it depends on the dimension. I mean depending on what is the bubble speed, that means what is u. Okay, you can find out depending on what is the value of r, what is the value of sigma. Okay, so if you know these values, you can probably find out what is the capillary number, and from that you can find out what would be the film thickness, what h we are referring to, that can be found out here. So, whether it is that means whether this portion, this annular portion is 1/10 of the actual dimension of the channel, or 1/100th or 1/1000th, that understanding you can get from this scaling. And one thing I must point out before I move to other topics is that nowhere in this analysis the contact line resistance has been considered. Okay. But still, I mean, you have a pressure drop because of two immiscible phases present in the channel, but it is not a contact line resistance. Okay. So, that needs to be understood here. I mean, we are not talking about the contact angle, we are not talking about the hydrophobicity, etc. So, we are just talking about, we are not talking about these contact line resistance. I mean, that is one assumption in this entire analysis, but still you have a pressure drop just because you have two immiscible phases flowing. Okay. Now, in the last class I just mentioned probably one line, that there is some interesting issue here of these flow of two immiscible phases through a microchannel, if you want to induce the flow through the through say electrokinetic mode. That means, if you want to have an electroosmotic flow of these two immiscible phases, if you want to have electroosmotic flow through this microchannel, then there are some points that would be that you need to consider here. So, what I let us write this here. What we are discussing, we are going to discuss is electrokinetic flow with bubbles. That means, you have this microchannel, you have a bubble placed axis symmetrically, and then you have an electrode here and you have an electrode there, just the way you have conducted electroosmotic flow or in the electrokinetic flow. So, you have these electrodes here, and you want to induce a flow. Then what happens if you do this? The problem here is that in case of electroosmosis, velocity u is equal to minus epsa zeta e divided by mu. This is these expression we have already we have, this is called electroosmotic velocity. These expression for velocity we have derived some time back, not in last to last classes, but some other in an earlier part of the lectures. So, lecture series. So, we have this expression there. This defines the velocity under electroosmotic flow. Now, if I look at this term E, by simple current voltage calculation, in longitudinal direction, E is inversely proportional to area of electrolyte across capillary. I hope you can appreciate the fact that here in this case you are applying voltage, but voltage means you are basically, say for example, I have NaCl here. So, NaCl breaks down into Na plus and Cl minus, right, and these are the ions and they would be responsible for movement, right. Now, here I am talking about this much of cross section for the liquid and this much of cross section for the liquid. So, this case the electric field E that you get and the case where you have the entire channel filled with liquid, these two would be different, because it is you are applying the same voltage. Okay. Same voltage is applied, but over a smaller volume of electrolyte in this case and a larger volume of electrolyte in the other case. Okay. So, when it comes to, you are applying the same voltage, but when it comes to the electric field that you get, that would be proportional to the area of electrolyte across capillary. So, what this means is, what this implies is, if this is the velocity, if this is the expression for velocity, then you can say u is proportional to 1 divided by this area. All right. now you have on the other hand the flow rate. Flow rate is basically U multiplied by area. All right. So, what you will have here is then flow rate is equal to, since U is inversely proportional to that area. So, flow rate will be equal to independent of cross sectional area. So, what the implication of this would be that the flow rate here where the bubble is not there, the flow rate here, okay, and flow rate in the surrounding films, that would be same. So, what that means is that flow rate behind the bubble is equal to the flow rate in surrounding film. So, what this implies is bubble remains stationary as electrolyte solution flows around it. So, that means the bubble remains stationary, but the liquid will be flowing around. I mean, you increase the voltage, you expect there would be more there would be movement, but it would be the liquid that would be flowing through the surrounding film, but the bubble will remain in that same position. So, this is one issue with electrokinetic flow with bubbles. This appears to be very interesting. Okay, and this does not happen in case of a pressure driven flow. So, that you must understand there is a difference. So, the remedial measure that is there, I mean remedial measure that has been studied here is remedial measure that researchers have thought about is add ionic surfactant that develops electric double layer at liquid air interface. If it is a bubble, liquid air interface, this is on top of, I mean this is in addition to, mind it, because already you have some electric double layer in addition to EDL on the wall, because to implement electroosmotic flow, you have to have an electric double layer at the wall, and that is how you are dragging, right. So, here in case of here you have ionic surfactant that is added to develop over and above this electric double layer on the wall, which is responsible for the flow. You have additional electric double layer at liquid air interface. Now, relative sizes of these two EDL, that means, so what is the size of EDL? We know as far as the size is, that is basically d by length. So, the relative size of these two electric double layer, one electric double layer is at the wall, which is responsible for the electroosmotic flow, and the other electric double layer is at the liquid air interface. Now, the relative size of these two double layers, that means the d by lengths of these two double layers, that becomes responsible for, that basically determines the determine the motion, determine the bubble motion. Okay. So, this is one issue which you need to know. I mean, when we are talking about immiscible flow of immiscible phases, the pressure driven immiscible flow and the electrokinetic immiscible flow, they have some, there is some difference between the two. Okay. With that being known, now I want to spend some time on the formation of these droplets and bubbles. I mean, that is also equally important. How will you form these droplets? How will you form droplet of certain size? Now, when it comes to this, I mean, when I go to the literature, what I find is that a common way of forming a droplet would be something like this. You have a T joint. Okay. You have one fluid which is flowing, say, which is flowing, I am calling this carrier fluid, which has a flow rate of q c dot, and I have a droplet phase which is flowing at a flow rate of q d dot. Q d dot. Okay, so, this is the droplet phase. Okay, now, this droplet is coming out, and this is, on the other hand, you have this carrier flow, and what you would be getting is droplets, then another droplet. Okay. This is a common way of forming droplet. This is referred as a T joint, because though I mean I should have drawn it, this arm should have been on the bottom side, then it looks perfect T. Anyway, you can invert this and you can still feel how it is T, how it is T, you can still feel here. Okay. Now, this one you have here. Now, you have the carrier fluid here and the droplet phase here coming in. Now, what you would be interested to know is that what you would be interested to know is that what are the forces responsible for generation of this droplet. Okay. For that, I must point out that there are two regimes possible when it comes to formation of droplet. When it comes to formation of droplet, there are basically two regimes. Okay. One is called shear regime and the other is called squeezing. And there is a critical capillary number which determines you are in which, I mean the formation of droplet is in which regime. If it is, if the capillary number of this whole formation process is less than capillary critical, then it would be a squeezing regime. On the other hand, if it is greater than critical, then it would be shear regime. In fact, I should put a equal to sign somewhere, because then you may say if C is CSGR, how will you account that? So, somewhere it has to be put then. The critical capillary number, it is typically its value is 10 to the power minus 2. Okay. What is the difference between this shear regime and squeezing regime? Let us first talk about the shear regime, which is easy to understand here. the process works like this. You have a flow of carrier fluid. This is called carrier, and there are other there are two phases. So, they are differentiated as C and D, carrier and droplet phase. So, you have this flow of carrier fluid. So, this carrier fluid imposes some drag on these droplet phase. Now, one analysis, I mean a very common analysis suggests, I mean if somebody wants to know if I have Q C dot is this, Q D dot is this, and capillary number is this, what would be the size of the droplet? And for doing that, for shear regime, a simple calculation would be that the drag force by this carrier fluid is equal to the interfacial tension. What this means is that this fluid is growing, but this fluid is held up by the interfacial tension here. So, when this drag force is more than the interfacial tension, you can expect, that is the threshold point when this extended plume that has come out of this arm, that would detach, and then it will continue as a single droplet. So, F drag is equal to F interval. This is a common way somebody can find out, a quick way of finding what would be the diameter of the droplet. Now, drag is typically given by half C D rho U C bar square into A D, where the A D is the projected area. So, A D would be equal to pi d droplet square by 2. So, that is droplet square, diameter of the droplet square by 2 pi what no if this is the area, that means it would be pi d square by 4. I should not be taking it by 2. Let me point out the dimensions here. I have this dimension is given as DC, that is the diameter of the capillary. The diameter of the droplet, I mean this does not necessarily fill the entire part of the channel. I mean in fact, the drawing is little bit, it should be a portion of the channel occupying, and this diameter is DD, diameter of the droplet, okay. And then maybe this diameter would be DI, this diameter would be DI, the injection port, this diameter would be DI, okay. So, I mean what you are doing, we are going to do here is we would be equating this with CS pi di sigma. CS pi di sigma, you understand, di is this basically this is the diameter of this is the diameter of the arm, and this perimeter is holding by interfacial tension the droplet phase at the time of detachment. So, pi di sigma I can understand, and on top of that you have something called a CS, which is some constant. CS is some coefficient, CS is some coefficient, CS is some coefficient accounting say cos theta, then shape of the injection port. So, there are something which we are not accounting here. So, that is clubbed into this parameter C s. So, C s pi d I sigma, I mean if it comes to this, you can take C s as 1. I mean it is like that Venturi coefficient you have, I mean people who are from fluid mechanics background. So, it is a similar one. So, you can have a C s, that is fine. This part I understand, and this part is drag. Why it should be pi d d square by 2, the area the area would be pi d d square by 4 actually, but that is at the time when droplet has been fully formed, and it would be 0 when droplet has not formed. And I do not, but at the time of droplet formation, however, the plume this that you have here, these may not take the full, I mean this, say for example, if I look at this dimension here, it would be something like this. It will take a shape like this, in fact, then it would take a shape like this, and then it would break. Probably we will try to touch upon this point, why you should be having this, or let me point, let me see what would be the final result in this case. C d for a hard sphere model, using hard sphere model, C d is equal to 24 by Reynolds number using hard sphere model. So, C d would be 24 by R e. In that case, the what would be the droplet diameter? What would be the droplet diameter in that case? It would be, I mean it would be definitely C s divided by C d. I see the value d I appearing here, then sigma is there, and if it comes to R e is based on the carrier fluid. So, this R e is nothing but rho c u bar d c divided by mu c. Okay, we can call this u c bar if we are talking about talking about u c bar here. So, this is something we have, and d I sigma divided by rho c u c bar square. So, this is something we have, and on top of that I have a factor here. All right, on top of that I have a factor here. That depends on what projected area you take for this droplet. I mean if you take these as 2, then it would be probably 2 into 2, it would be 4. It would be 4, and it goes to that side. So, when you take the square root, it will come out as 2. That is a possibility. Now, if somebody assumes C s to be equal to 1 and C d to go there, then the droplet diameter would be, in that case, would be equal to, then you have square root of sigma divided by mu c d c d I divided by u c bar. If you bring in this Reynolds number, I think you take C s as 1 and C d as 24 by R e, this multiplied by 2 if it is taken as pi d d square by 2. So, this is basically the equation for droplet diameter, which is equal to, the functionality here is we have capillary diameter DC is there, we have di is there, that is the diameter of the injection port, that is there. We have UC bar, the average velocity of the carrier fluid, which is nothing but QC dot divided by pi DC square by 4. So, that UC bar is there, carrier fluid viscosity is there, interfacial tension is there. So, that gives the diameter of the droplet. So, if somebody wants to produce droplets of certain diameter, he can choose the dimensions, he can choose the velocity of the carrier fluid, and he can come up with the right dimensions. Okay, that is possible. Now, this is what you have, what I called is shear regime, right. We have another regime to talk about. Now, it is one thing I must point out, that when you are working in shear regime, then when you are forming droplet like this, it has been found from imaging studies that there would be some shear going on inside the droplet. I mean, after the droplet forms, if somebody there is a method called PIV, particle image velocimetry, where you can put you can see what are the velocity vectors within this droplet, and you will find that this droplet, because of the formation process itself, the droplet after it formed, after you see an isolated droplet, if you study, you will see that there is a vortex inside the droplet, because you are producing a shear. Look at it, the carrier fluid is shearing it, right. So, within the droplet phase itself, there is a shear. So, if this is the droplet phase, if this is the droplet we are talking about, you will find that there is velocity profile like this. There is a vortex generating within the droplet itself. In fact, this is why there is a proposition that these droplet can be used as a mixer. That means, you have two streams, you mix them, you put them together, and then you want them to be thoroughly mixed. So, you put it under this regime, and you will find, because of these small micro vortex inside the droplet, you will be carrying out mixing. So, that this is the one mode of mixing the researchers have suggested also. So, this is a possibility. Now these once again underscore the fact that this process is shear regime. That means, since you have the shear, so that is why you have caused this type of movement within the droplet. So, the velocity vectors, if somebody tries to find out, he will find a substantial development of vortex inside this droplet. On the other hand, in case of squeezing regime, I do not expect shear to get into this. So, this would be forming, this would be again a T joint, same thing, only thing is the shear would be absent. So, if you ask me, I mean, how do I know capillary number is greater than CSCR, that it is the shear mode that is responsible for the breaking up, that already researchers have observed within the droplet, that there are remnants of that shear already present at the downstream. So, now I must talk about the squeezing regime. In nutshell, what squeezing regime is here, that this thing grows, this droplet phase grows and hits the wall. It fills this channel completely. Then in that case, where will the carrier fluid go? The carrier fluid will start eating away, or carrier fluid has to push it, right. So, you will find that this has formed, this has filled the channel. Then you will find that this is taking this kind of shape. The droplet has advanced a little bit, and carrier fluid is pushing it further. Similarly, so carrier fluid would be pushing it, carrier fluid cannot pass by the side of it. There could be some leakage that is negligible, but predominantly beyond this point the job of the carrier fluid would be to eat away this portion. So, that means it was originally the droplet was forming like this, and this is the di, this whole thing is the di, but at next moment this is taking this kind of shape, this is di, and this QC is pushing the liquid. Okay, so it is squeezing, that is why it is the squeezing mode. So, it will continue to squeeze, and at some point these thickness would be too small, and then probably I mean, if you want to consider it, you can look at this Rayleigh plateau instability, or otherwise also you can find out how long it takes for this to from the geometric consideration, you can find out how long it takes to reach the end, because moment the end is reached, the droplet is released. So, it is completely, you can find out the entire analysis would be based on geometry, and if you will the Rayleigh plateau instability. I mean, if you do not want to give the from geometry, you can say when this thickness gets 0, because this QC dot that you have, that is fixed, that is constant. So, it has to eat away, and rest of it is geometry. Now, you can say that okay, it will reach the end. When it reaches the end, I will consider the droplet to be released, or you can say that okay, still there is some delta left, and at that point some Rayleigh plateau instability caused this to rupture, because here it is a neck, here at this point, here it is a neck. So, at some point there is a rupture. So, but anyway that delta would be very small. So, this is coming purely from geometric consideration, geometry, and you have to satisfy the QC dot. If you assume that there is no leakage around, so QC dot cannot pass by. So, QC dot will be eating away. So, from geometry wherever it goes, and it goes that way. So, that defines the diameter of the droplet. Okay. So, that is exactly what is squeezing regime. So, you are not shearing the droplet, but you are doing it this way. So, this is the difference between the formation of this is the difference between two droplet regimes, I must say. Now, typically if somebody wants to find out what would be the dimension of the droplet, it would be from the point of view of from the point of view of geometry, that is for certain. I mean, one can, I mean, if time permits, probably I will talk about it further, but that how this geometry can be applied to find out what would be the diameter of the droplet. It may not be a simple analytical form like this, the way we put it here, but let us see. I mean, for the time being, let us just appreciate that there is such possibility, there is such regime, and you understand how this regime works. I think that is important, and later on we will see how we can make use of it further. Now, there is another possibility which goes by the name Lambda Junction, okay, which goes by the name Lambda Junction, which is something like this, that you have a T joint, okay, and you have you have an inlet here, you have an outlet here, and you have another outlet here. Okay. So, you have the droplet phase coming in and droplet phase is forming. So, you are forming the droplets, fine. Now, you are collecting, you have a possibility of collecting fluid through this side, you have a possibility of collecting fluid from this side as well. So, what will happen is, once this droplet comes and reaches here, so it will tend to take what shape? It will go like this. Do you agree with this? This is the type of shape it will take. Okay. So, this is the type of shape it will take, and then you have, depending on what is the pressure here, what is the pressure here, and what is the pressure here, it can, one possibility is that it can go in a little bit and later on it negotiates and it just simply comes out. It goes in, and then you have interfacial tension which is pulling the droplet phase together, because you have a, why is it a sphere? Because there is some reason to be. So, why is it intact? Why is it a droplet? Why it is not a completely dispersed one? Because it has a reason to it. I mean, it has surface tension holding it together. So, that will negotiate. I mean, on one hand you are trying to push a portion of the droplet out, on the other hand you have the surface tension which is trying to pull it together. And so, basically bottom line is that the back side of this droplet, if this is the front side and the back side of the droplet, you are stretching, this side you are stretching, all right. So, once you stretch this, if you stretch this too much, then you can expect a daughter droplet forming out of it. So, you will see this portion is stretched too much, that means you have a droplet of shape like this, and this layer is stretched too much for this. So, this layer is gradually it will go like this, and then this thickness becomes they are too close to each other, this corner, because of this Raleigh plateau instability. Then you see that this is forming a droplet and going in. So, this is referred as daughter droplet. So, this is the major droplet. You are already in the microchannel and you are in a microscope. I mean, you are forming small droplet, but if you are interested in forming a smaller one, then you can negotiate between these two flows, and you can literally form something called a daughter droplet. On the other hand, if you have a pressure here, you have a pressure here, and you have a pressure here. So, if the pressure is not, if the pressure differential between this point and this point is not sufficient, then what will happen is it will go in a little bit, but it is not gone in sufficiently. So, it will retract and again proceed just like a droplet, and again this would be forming like a droplet. So, depending on how you play these three pressures, you can be forming daughter droplet or not. I mean, that your will. Okay, so, and this droplet is expected to be much smaller, because it is originally you formed a droplet and then you chopped off a small portion of that and putting it as a daughter droplet. And this, because of this shape of this as this device as lambda, there is an angle to it. You give this the name of this is given as Lambda Junction. Now, there are certain theories already put forward where what you consider in this case, because since you are in this squeezing regime, this entire formation process is in squeezing regime. So, one thing you must understand, that what you are doing here is simply you have the flow rates here. Okay. One is, say again a carrier, or you write it as this q I, q O and q D, where this is say q D, this is say q O, and this is what is coming is q I. So, again you are, and depending on the relative values of this q I, q O, q D, and a geometry consideration. That means, what is this thickness, what is this angle, okay, and what is this delta, that up to which it can go and beyond which there would be a rupture. Okay. So, what is this delta beyond which this becomes unstable. So, so other than these, what you need is geometry. That means, the dimensions of the channel, the angle and that delta, etc., that governs something called the LC, by up to what extent what is the length of this back part of the droplet that has been stretched, okay, and that governs. So, these factors primarily, since you are in squeezing regime, you do not need to consider shear here. These governs what should be the diameter of the droplet, and moreover, I mean, you don't need to write Qi, Qo, Qd. You can write simply Pi, Po, Pd, the pressures at this point. So, pressures and the geometry, that would govern what whether, no, most importantly, whether you form a dotted droplet or not. Okay. It could be that that Pi, Po, Pd that you choose and the geometry, that is and geometry, and of course, sigma, very importantly. So, that the values that you choose, the matrix that you choose, is not capable of forming a dotted droplet, then you see some introduction of droplet phase into this other arm, but then it is again pulled and continued. Whereas, if you tinker it further, you may see under some configuration you are forming dotted droplets. So, this is a very interesting point here. If I wish I can discuss the squeezing regime more if possible. Let us see. Anyway, that is all I have for today's class, and I will meet you again tomorrow. Thank you.